Alright, so I'll be explaining the solution to this problem called Cyclic Mex. And I can actually explain what the problem is because it's a very short problem statement. It's basically you have an array A, and you want to, the cost of this array is just you iterate through all the prefixes and you find the max, the minimum element not excluded in that prefix. And then you that's like the element, and then you add that element up for all the prefixes, right? So a pretty straightforward problem in terms of understanding it, and you're given a permutation. So you want to solve this problem in the context of permutations, right? You want to sort of emphasize the fact that the permutation is all numbers from one to n in that permutation have to appear once, or 0 to n minus 1 in this case. And then you basically want to find the maximum cost considering all of the n cyclic shifts of this permutation. So nothing going on crazy with the constraints. We just have n is 10 to the 6th. So constraints are not going to be really an interesting part of this problem. But what is pretty interesting is the first thing I thought about is, well, the first thing that I actually did was I took this array, and for every cyclic shift, I basically wrote out everything. I wrote out the entire process of like every prefix for every cyclic shift, right? So there's like, in this case, there's like 6 arrays you would write out, because there's 6 places you can start the array from, and then just go right until you um uh circle back around. There's 6 different places you can start, and for every array I wrote it out, and I also wrote down all the cyclic shifts, or I mean I wrote down all the prefixes, and then they're the max, and then I added up. I basically wrote out the brute force solution, which would literally be finding all these arrays, and then iterating through all the prefixes and finding the max and then adding up. I wrote down everything for this, and I did notice some nice things. I thought that was a pretty, active way to play around with the problem. But one thing that I did realize that I ended up doing, one thing that I realized is that this condition over here, and I guess I should have realized it first. So this is really in the mindset. Whenever again they give you something like this, it's good to think about how you can say it differently, or like, can this be simplified? Right. Can the process be simplified? Right. The cost, right? The process of finding the cost, can it be simplified? And it can, because here's a very let's just say you have this permutation, and I'm gonna write it down here. Let's say it's just like 5 4 3 0 1 4. You notice that when you're finding the cost, effectively what you're doing is you're just, because if you have some prefix, right, and you want to find the minimum element it's not included in this prefix, then it's basically just finding the minimum element in the suffix that connects that prefix. You know what I'm saying? Because basically at the prefix from 1 to I, right, the numbers that are not included in that prefix, right, are the numbers that are not included in that prefix are the numbers that are included in the suffix, right? The suffix represents the numbers that are not included in the ith prefix, right? This suffix 014 represents that these numbers are not in the ith prefix, right? And so the minimum, because this is a permutation, right? This is the only way. This is the only reason this can hold, because this is a permutation. Then you basically can say that the minimum element not excluded is just the minimum element in this suffix, right? So it's just going to be like 0 here. And this whole, so basically what I noticed in this problem is the cost is basically just equal to n, and then plus the sum of all suffix maximum, or of all suffix minimum. And the reason it's n, because you need to add, when, I mean, there is no suffix here, so that just gets n. That gets just to be n, right? But then for every other suffix, for example, like 4, and then 4 and 1, 4 and 0, 4 and 2, 4 and 3, 4 and 5, it's pretty much just n plus all the suffix minimum. For every other prefix, that's not the entire thing, right? It's just adding up suffix minimums. And again, this only holds because this is a permutation, right? Again, it's pretty obvious that if you want to find the number that's not included in the I prefix, um, the numbers that are not included are obviously just in the suffix, so you just find the minimum of those, and that's a minimum element that's not included. So that's by definition. If this was not a permutation, this would not work because the suffix doesn't fully represent the numbers not included, and um, it's not unique. So a permutation actually makes this this sort of property, like this cost property, right? This is more vague, right? This is more vague, but you can actually, because you have this condition, right, that the array has to be a permutation, you can specify the cost to be exactly this. So this specification, this specifying of the condition into this, basically what it does is that it abuses the fact that this is a permutation and it makes it more specific. So that's basically the observation I noticed. I guess you can come to this observation. I mean, I noticed it personally myself, but you can come to this observation by just thinking about the process of finding the cost. Like when you think about literally the process of finding the cost, like when I just realized that I'm basically just taking the suffix minimum because all the elements that are not included are simply this. And so it's pretty easy to come up with this conclusion. But again, it's just being in the mindset of simplifying what they give you and reducing it and making it more specific in the context of the problem. And so, yeah, I came up with this observation, not really directly trying to do it, something like that, or reduce the condition. I just wrote out and I just literally did the process, and I figured out that that's basically what this means. Okay, so another thing that I realized out when I so this is a really big observation here, I think, right? Another, that's why I spent a lot of time on it. Another thing that I also realized when I wrote down like the brute force process is that at some point, right, wherever the position 0 is in your cyclic shift, right? Obviously, when you take suffix minimums, like it does not matter what you do, the suffix minimum it already hit rock bottom, so you can't decrease anymore, right? Once the suffix minimum crosses 0, it's just going to be 0 0 0 until you get to the end of the array. So this means that basically, um what we notice here is that you'll what's happening is you're basically just having a bunch of zeros, right? And then you're just gonna add like some actual suffix minimums. So maybe you actually add some actual suffix minimums, but that's basically what the cost is gonna look like. Maybe you add n or something, and then you add a bunch of suffix minimums, and then you add 0. That's pretty much what's going to happen. Um, but what I thought about when I did this problem, when I looked at this 5 4 3 2 1 0, I thought about thinking about the array at where 0 starts. Right, 0 is a good reference point, right? Because the reason why 0 is a good reference point is if you think about, okay, so let's say 0. Let's just say we have some random array, right? Just in general, right? 0 starts here, and we have some elements. Maybe we have a1 after 0, and then we have a2, and then we have a3, all the way to ai. Um, all these elements over here, they don't matter. These elements literally do not matter at all. The reason why they don't matter is because when you're finding the cost of this array, those, like at this, from 0, from the pivot, when you make set the pivot to be 0, from that pivot, after that pivot, all those suffixes are gonna like just literally be 0. So you don't care about that, right? So when you think about it, what you can think about this is that what we want is we want to find, because we want to find the cost out of all the cyclic shifts. So basically, what we can basically say is that what we're curious is we want to find cost I, where um, we have appended exactly I elements after 0. What this means is that, because if you think about it, right, you can think about a cyclic shift not really in terms of like, because every cyclic shift it starts at 0, right? But the idea is that like you can think about it as it looking something like in this, right? So for example, let me just make this more concrete. So if you look at this element here, this array here, right? So you know what you observe here is that you notice that it starts at 0, right? But these elements don't matter, right? For this cyclic shift. Now if you move it to the left, it starts at 0, 1, 4, 5, and then you add 2, right? You get 0, 0, 4, 5, 2. And then these elements here, they don't matter at all. So what you can think about the cyclic shifts is just basically appending a new element after 0. So if you think about 0 in the last position, every time you move 0 to the left, you can think of just appending a new number to the end of 0, right? And then you can think of every time you move it to the left, you just append a new number, because in that way you can think of these stats, how you can think of these cyclic shifts, right? And the motivation behind this comes from the fact that you notice that when you're doing this process, right? You notice that at that point the suffix minimums become 0. So why do you don't care about those elements? Those elements don't actually matter. What you really care about are the element in the cyclic shift. What you care about are the elements that come after 0, because that's not we don't know, because they're actually going to contribute to the cost, right? You only care about the elements that actually help you contribute to the cost, and those are the elements that are after 0. So when you think about these cyclic shifts, you really think about where 0 are, what are the elements after 0, and what we really want to know is we want to find, like, provided, let's say we want to find cost I where we have appended exactly I elements after 0, right? And let's have this assumption, right? Let's assume, right? And let's assume that we already have the answers from 1 to cost I minus 1, or from cost 1 to cost I minus 1. And the reason this is true, because this is sort of the DP mindset, right? You want to find the cost I bear. We're basically finding the cost of the array, given that the cyclic shift, given that we have appended exactly 1, because we can think about, just the cyclic shift of 0, and we can think about like appending 0, 1, and then 0, 1, 2, and then 0, 1, 2, 0, 0, 1, 2, 3, right? We basically say we want to find the cost of this array after we've appended exactly I elements after 0. We're just rewording this sort of question, right? And let's assume that we already have the answers from cost 1 to cost I minus 1. Okay, so now that we sort of reworded this question, what we want to think about is, how do we actually solve this problem? So in this case, what we notice is that we want to find basically the answer, right? This is cost I. We've appended I elements. If you think about it, you want to say, okay, so you want to just think about it like this. Okay, so to solve this problem, what you need to do is you first need to find the suffix minimum from AI to the suffix minimums. You need to add the suffix minimums. So first, you realize that cost I, it's just like you add AI, and then maybe you extend this, right? You extend this here, and then maybe the minimum is still a sub I, and maybe the minimum is still a sub I, maybe the minimum is still a sub I. You keep adding a sub I until you get to some index j. So basically, when you're finding cost of a sub I, you keep adding this until you get to some index a sub j, where a sub j becomes uh until you see a sub j become greater than or become less than a sub I. At that point, you know that it changes. But then if you think about it, a sub j becomes the minimum element, right? If a sub j becomes the minimum element here, then what you're doing is you can pretty much just say, uh, to find the cost, you could just say it's just going to be, cost is going to be basically a sub I times I minus j, because you go from j plus 1 to I. Um, there's I minus j elements, and all those have a minimum of a sub I, and then you can just add cost of I, or then you can just add cost at j, because then you know that pretty much here you're starting a new problem, that you've already solved before. You're just saying that you're starting on a sub j, that's your minimum, and then then the other numbers here, they don't affect any, like when you go and do the problem again, like these numbers don't really matter, like because this is the minimum, and then you're just like processing it, and then boom, that's it. It's only going to change if it's smaller than a sub j. So you realize that you have this really nice relationship that cost I is actually equal to a sub I times I minus 1 plus cost j, plus that the first element that you see when you start moving left that actually becomes smaller than a sub I. And we can, this is fine because we've already assumed that we have our answers from cost 1 to cost a minus 1. And so then the only thing that really remains is how to code this. It's actually pretty simple. All we have to do is we just got to think about from 0, we make a new array where we just add like all the elements after 0 or whatever. Um, like we just go here and then just go here. And then what we just do is we just sort of loop through. And then all we need to really do is we just need to see how we just need to query like um, we basically what we need to query in this array is the only thing we need to query is first of index I, find the largest j that satisfies a sub j less than a sub I, and j is less than I. So find the largest j. Find the largest j. This is what we need to query. We might need to query like find largest j such that a sub j is less than a sub I and j is less than I. This is a very common question. You can use a monotonic stack. This is just implementation details. That's just implementation details. But yeah, that's pretty much just the solution to this problem. You can see that it's a pretty simple question. That's the only thing you're gonna have to really query, and you can pre-compute this, and then boom, it's just simple. It's literally just simple. It's literally just simple. And if you don't find an index, if you don't find this j index, then you can just assume that the max is a sub I for all of them, and then that literally just works. Yeah. So this problem works. Because this is the cost. Also, we have to be careful with how we define this. So, um, yeah, but that's pretty much it. But yeah, let's implement this, and then we can talk about sort of let's implement this first. But I guess I'll talk about sort of how we figured out. So I'm gonna implement this, but and then we can talk about this. But really, this just came down to rewording the condition they gave you and making it sort of more straightforward of a problem by sort of rewriting the question in a way. But yeah, let's do this problem. So what we need is what I'll do actually is I want to create a new array. This new array is going to be this is going to be b, and basically what b is you need to find where the index I is. So you need to find where index 0 is. So this is where 0 starts, right? So what you do is you locate, right, and then you say if a sub I is equal to 0, you say index 0 starts at I. Okay, so what you want is you want the first element to be 0. That's what you want. But what you're going to do is you're going to start at index 0, 0 plus 1, and you're going to mod n this. So index 0 plus 1 Or actually, or you keep going. Okay, so actually, you keep going until you reach the 0 because you don't want it. And then what you do is I'm actually gonna mod this by n. Okay, yeah. So I'm gonna create this new array b, and what's going to happen is I'm going to find where the index 0 is. So you loop through and you realize that at I, the index is that's where it's 0, and the index 0 is that's where it's 0. So you find it and then you start at +1, and then you realize that you take you basically or I what I would do is I would just have some pointer 0. It starts at 1, and what you do is you do this, and you basically start. Um, so you start at index, and then you add 1, but then you have to modulo n it because it could like because it could start at the end, and when you add 1, you want to start it at 0, and then you just keep going until until you don't, because you don't want to actually get to your index 0. So you just keep going, and then you said I plus 1 mata, in case it like goes out, it would go back to 0, and then you just keep going, and you don't want it to get to index 0. So and then you set this to your AI. Okay, so then we can just, honestly, let's just test if this works. So this just gets the array that we need. B is just some array transformed. So let's just test if this works because, I don't want any problems. And this is because 0 is like our reference point. We're like referencing the array at 0, and we're just thinking about appending elements after 0. It's sort of okay, so it works. Unsurprisingly, it works. Okay, so now what we need to do is we need to query how to find the largest j such that the way we'll do this is we'll use a monotonic stack. Uh, so the way this works is, I think if I remember correctly, quickly think about how you do this, is you have this element I. These are the elements you want to consider of being smaller than you. Uh, if you just put these elements on a stack, like um I need to remember how to do this. So I think it's like you want elements that are you want to find previous small. That's what you want to find, right? Um, and you want to. So the way this works is what you notice is that when you're at I and you want to move backwards, right, to find some element j such as the smallest one, uh, you notice that um, if this doesn't work, this doesn't work, this doesn't work, this doesn't work, J is here. When you go to I plus 1, either I works, and if and this what this implies that these are greater. If I doesn't work, then obviously these are going to be greater, so you don't need to consider it. So pretty much you can just like low-key simulate this, but when something doesn't work, just don't let it work. You know what I'm saying? Okay, so it's just going to be the previous smallest element of 0 is obviously just you don't have a previous smaller element. So previous smaller element of 0 is obviously -1. So this is where it's sort of nice to have, but you can do indices dot add, and you can add 0 ends. I like ends way better. But yeah, ends the add 0, and then for every element you want to find this quantity. This would be the previous smallest element. You put this on the stack, and basically it's just like while ends dot while is not ends dot is empty, right? While this is not empty, and the element at the top of the stack that you're considering. So ends at peak top. Peak. Ends at peak. While this element, or you want to use it for B. While this element itself is greater, right? You don't have to worry about greater than or equal to. It's just greater than the element that we were talking about. Then, while it's a greater, then just keep removing it. Literally keep removing it. Say that ends dot remove, right? Or ends dot pop, and then you just keep popping it, right, until it doesn't work. And then if ends dot is empty, right, then we say that the previous small element at I, there is no element that's smaller. This is the minimum. Or else we say previous small at I is whatever we have here. It's whatever we have here. Dot peak. Let's just check if this works because I don't want to do this. Yeah, I'm not trying to debug this, so we're just gonna check if this works. This is completely descending. It's pretty boring. This is hella boring. What? Yeah, we didn't do that. Yeah, that's why. Previous smaller is just going to be 0 here. Previous smaller is going to be 1 here. Previous smaller is just going to be 2 here. Previous smaller, which is 3, is just going to be 1 here. And then previous smaller here, which is like next. What is it? Like there's 8 elements in next 6. That's just going to be next 5. Okay. Seems like it works. Previous smaller here. Yeah. Okay. So this works now. And then all we got to do is we're going to define this cost function. Um, technically, yeah. So if you append 0 elements after 0, then you have just like the cyclic shift 0, and basically what happens is that if you have 0, everything, like if you just have 0, like everything just becomes 0 except for the thing itself, pretty much. So it's just cost at 0 starts at n. And the reason this is true is just because like all the suffix minimums will be 0. It's just n plus all the suffix minimums, and that's just obviously just 0. They're all just gonna be 0. Yeah. Now we can append 1 to n minus 1. So what we want to do here is we need to find this index j. Index j is given by the previously smaller element of I. Now, if j is equal to -1, then we realize that the cost at I is simply just going to be it's just cost of 0 plus yeah, because you can pretty much just like, I mean, 0 is gonna be, wait, a 0 should always be smaller because 0 is the first element. This should also be at the back. These are all indices, right? Oh no, never mind. This j equals -1 doesn't even hold. This only holds if you do something like previously smaller of 0, which is not what you're gonna do. So actually, cost at I is basically just cost at j, and you have I minus j, and then you have a sub I. Isn't this literally just it? Is this literally not it? Wait, what the fuck? That seems like a very simple. Yeah, it is. It pretty much is. Yeah. Yeah, it really just comes down to using a monotonic stack and you just like plug in the formula. Okay, I got cooked. I got cooked. What? Oh, it's B. 15,531,0. You have an edge case here. It's an edge case. would this print out 0? I mean, oh, is that just is that just an edge case if the only element is 0? Oh, that makes sense. Yeah, hopefully this just works. Because I got a dip. Alright, nice. It works. Cool. Yeah, so, yeah, that's a really good question. You can think about how we came up with this, but it was pretty much just you had to simplify the condition that they gave you. So this is just the code. Pretty basic here. Pretty much gotta just do monotonic stack, and that's literally the only thing. And then after you just nicely plug stuff in, like pretty much it. But you had to think about the condition they gave you, right? The condition they gave you was this. You had to simplify it, and then you had to sort of reword the question. It was really this observation. All right, got you. All right, now let's end the video.